Always a pleasure to be here in the Skyscraper Museum, and particularly in the sort of final weeks of this exhibit, which was a great challenge from Carol to think about what is the modern concrete skyscraper, and can we tell a history of a building type that historians have typically looked at as a steel phenomenon. Um, as she said, the project really started as the second book was finishing up. I brought to the table a kind of knowledge of high-rise history, Chicago in particular, and Carol's charge was basically to think about the skyscraper in broader terms, and to think about it as a material phenomenon, but not just about steel, also about concrete. And the key moment for what I'm going to present tonight was, as we were putting together the timeline, Carol was the one who looked at it and said, you know, there are an awful lot of buildings here that are from Chicago, right? Chicago has a kind of outsized presence as we're looking at the tallest concrete skyscrapers throughout the 20th century. Is there a reason for that? And I couldn't come up with one initially, but we also realized that some of the buildings in the timeline were not in Chicago, but were designed in Chicago. And this ended up being the sort of challenge for the research that I'll show tonight. All good research projects ask more questions than they answer. And the exhibition really asked the question, like, what was it about Chicago that led to this particular phenomenon? And are there things we can kind of learn from that we can extract from it? So I want to go back to the beginning, really, of the 20th century and talk about the trajectory of concrete in Chicago. I want to focus not so much on the buildings themselves, although they play a key role, of course, but I want to talk about not just the engineers, but another set of professionals and experts that lent their knowledge and lent their kind of process to the quest for better concrete, and therefore the quest for greater height. Concrete in Chicago, I think you can trace back to the kind of American pioneer of reinforced concrete, Ernest Ransome. Ransome was a British emigre. His family ran an artificial stone business in London, and he brought his knowledge of concrete to first San Francisco in the 1870s and 1880s, and then eventually to New York, where he famously built a handful of warehouses that pioneered the idea, or pioneered his version of reinforced concrete. In between, as you can see from the advertisement here, Ransome spent 5 years trying to establish himself in Chicago between 1895 and 1900. He was a member of the Union League Club. He, as you can see, had an office in the Boylston building, and seems to have not been commissioned to do anything in Chicago. Steel was, of course, ascendant at the time, and so concrete was seen more as a fireproofing material than as a structural material. And Ransome seemed to get very, very little traction in promoting concrete in the city. These are some of his patents on the upper left. I think Ransome's contributions to the way we understand concrete reinforcing, the way that we build with it, are, even though they're acknowledged, I think they're still kind of understudied. And some of his patents look very familiar even today to those who design and reinforce concrete. His great high-rise achievement, of course, was the Ingalls building, for which he was the consultant and subcontractor. The Ingalls building was widely acknowledged as the first concrete skyscraper, and it was built not in Chicago, not in New York, but in Cincinnati. And even though Chicago had nothing to do with it, I think you can look at the first generation of concrete high-rises or mid-rises that go up in Chicago and see the influence of Ingalls. So here, as near as I can tell, are the first two reinforced concrete high-rises in the city. The Hayworth and the Bourne buildings were both mostly industrial, so they were like high-rise factories. And even though you see the kind of reinforcement in there, the rationale for concrete in factories was generally for fireproofing, not for reasons of structural efficiency. The material was relatively cheap. It could be built using carpenters instead of iron workers. And of course, it had a good track record by this point in containing fires, if not actually suppressing them. If you look at the proportions, you realize that concrete was not a particularly efficient structural material at the time. Those columns are sized to carry loads. They're not the kind of fireproofing around a thinner steel column. The concrete is chunky and it is relatively weak, and therefore the material really has to be used in bulk to hold up the floor loads that it's being asked to. Where there was innovation in the city was in a very different building type. The grain silos that populated the Midwest throughout the early 20th century were generally engineered by firms in Chicago. And concrete around the turn of the century became the material of choice precisely because it was fireproof. Timber grain elevators that had been built before 1900 tended to go up in flames very quickly. And concrete, as soon as it became kind of commercially viable, was used as a replacement for timber. So here you can see Jason McDonald, an engineer who specialized in grain elevators. This is one of his patent drawings for a construction method that today we would call slip forming. So this is a bit of concrete formwork done on a circular plan that's gradually raised up as the concrete cures, and so you can pour continuously from bottom to the top. And you'll see that come back particularly in one particular set of skyscrapers in a little bit here. The buildings that were built in the kind of late around 1910 or so, gradually you see a couple of things happen. You see the kind of skeleton frame that Ransom designed for Ingalls, and that were the kind of genesis of those early high rises. The skeleton frame kind of coalesces and starts to disappear. The deep girders that carried the loads in the Bourne building and the Hayworth building start to get distilled into flat slabs and what were called mushroom columns. So columns that flare out at the top, and the flare at the top is designed to prevent the column basically from punching through the slab, a phenomenon called punching shear. These are heavily reinforced, and you can see that they're starting to look for ways to make the system more efficient. The girders drop only a few inches, and this is a way to kind of increase the floor height. The slabs get thicker, the girders get shallower, and you can start to see them kind of coalescing towards what today we would call a flat slab. The flat slab was the kind of big desire in concrete construction because it stood to save on structural depth and therefore to save on building height. Flat slab is structurally thinner than a steel frame, and therefore you could get more stuff into your warehouse, or you could get higher floor to ceiling heights, say, in an apartment. The flat slab, though, is difficult to calculate because it's heavily reinforced and because the loads are being carried in multiple directions. It's what we call hyperstatic, and therefore, even though it's very efficient structurally, it's very hard to figure out where those loads are going. And Chicago, like most cities, struggled to figure out a way to encode flat slab construction. Here in 1911, this is from the Chicago Building Code, showing a very, very simple rule of thumb to try to calculate it. And here in 1918, a slightly more sophisticated version that sort of estimates the maximum bending moment, tells you what the slab depth ought to be based on that, but that isn't yet sort of theoretically based. This is still kind of an empirical method of guessing at the maximum stresses in the slab and then sizing them based on what's worked before. Allowing the flat slab and giving some rules of thumb for its design did lead to a generation of flat slab construction in Chicago. So mostly, again, for industrial purposes, a milk, a dairy equipment production facility on the left, the Sharples building, and a paper manufacturer that's still there now, nice lofts down on Printers Row, the Moser Company building. And you can see that the slabs are flat. They're not necessarily thin. In some cases, they're 13 or 14 inches deep. And because they're so heavy, you can see the columns have to flare out or to be thicker to take the so-called punching shear. It's about this time that academics sort of step in and start to see reinforced concrete as a place where they can contribute. And proud to say, one of the first examples of this, and certainly the most productive, is Dr. Arthur Talbot, who is a sanitary engineer hired by the University of Illinois to teach about sanitary engineering. And the material of choice in sewerage and in water treatment is concrete. And so Talbot gets very interested in the material from that perspective and begins conducting tests not only on the kind of sanitary qualities of concrete, but also on their strength. He develops a laboratory that is still on campus. This is his 3 million pound concrete breaking machine in the lab. Good fun. And he begins to develop theories that he can test in the laboratory to try to understand better how concrete, and particularly reinforced concrete, works structurally. And to his credit, he does this in two ways. He builds and breaks reinforced concrete beams in the lab, as you see on the left, but he also goes out into the field and wires up buildings with sort of rudimentary deflection indicators and tries to understand how they're actually behaving under load. So this is one of his first tests on a warehouse in Minneapolis. And then in 1909, he gets the sort of chance of a lifetime. There's a warehouse building that's constructed in the West Loop that has to come down because Union Station is expanding. This is on that site. And so Talbot comes in and is able to load it to failure. So you can see on the right, loading up one of these slabs with pig iron. It's a mushroom capped slab, right? So a very, very typical construction of the day. And what Talbot finds is that, in fact, the building is much, much stronger than the code says it should be. Here, a write-up that is sort of saying this is fantastic, right? Concrete is much better than we thought. Talbot, of course, sees this as a failure, right? There is 4 times as much concrete potentially as there needs to be in this building. And Talbot begins to realize, and people in his lab begin to realize, that part of the problem is that they don't understand the concrete part of the equation well enough. This is from the 1911 Chicago Building Code. And if you look at the figures that they're giving for the strength, the ultimate strength of concrete, you can see that it ranges between like 2,500 and 3,000 pounds per square inch. That's very low by today's standards. As we'll see, that figure gets higher and higher, but it's also a huge range. And what this implies to me is that no one really had a grasp on exactly how strong concrete was. Part of the problem is that this is also from the 1911 code, and it tells you basically it's a prescriptive code. It tells you exactly what the mix of the concrete has to be. And you can see that it's a proportion of cement to sand to broken stone or aggregate. And in particular, there's a mix that's 1 to 2 to 4. So 1 part cement, 2 parts sand, 4 parts stone. And you can see that the code says the ultimate strength of that is about 2,000 PSI. And it varies between 1,500 and 2,300 depending on how much aggregate you have there. But the error bars on this, again, are huge. And part of the problem that Talbot understands and that his lab begins to understand is that those error bars are part of the issue with understanding concrete. A graduate student in Talbot's lab, Duff Abrams, will later write a statement that I think really sums things up. At present, we know a great deal more about the properties of reinforced concrete than of concrete. And what he means is that all the study has gone into the ways that they put steel into the mix and the way that those slabs are formed, the way that they behave. No one has gone in and looked at the chemistry of the concrete itself. And that is what Abrams sets out to do. After he receives his degree from Illinois, he comes to Chicago. He gets a position at the Lewis Institute, which is a technical training institute. It will later merge with the Armour Institute to form the IIT, the Illinois Institute of Technology. But Abrams is there well before that, and you can see in his lab they're building or they're pouring various mixtures of concrete and then testing them to destruction. So they're less concerned with the reinforcement and more concerned with the kind of chemistry, right, or the recipe of concrete. It's an incredibly prolific laboratory. They churn out a couple dozen papers, one of which in particular, design of concrete mixtures. Portland Cement Association a few years ago did a poll, like what are the top, like 20 innovations in concrete. And this paper was listed in the top like 4 or 5. And the reason for that is that Abrams discovers, as he is preparing all of these mixes, that what's been left out of the equation, right? If you think 1 to 2 to 4, cement, sand, aggregate, there's a fourth ingredient, and that ingredient is water. And Abrams says to this point, the codes, the specifications have all said, just put enough water in to make the mix pliable, make it into a liquid. And Abrams realizes that this is actually the kind of key to concrete strength, that the more water you put into the mix, as that water is absorbed into the chemical reaction, as it evaporates, it leaves voids in the concrete and thus leaves weak concrete. This is a chart sort of summarizing his findings. And he says, basically, what you use for aggregate, how you proportion that aggregate, it doesn't really matter. We'll come back to that, not exactly right. But he says the much more important factor is how little water you can use in the mix. And up to a certain point, the less water you can use, the exponentially stronger that concrete will get. And this is the kind of realization that will form the basis for a lot of concrete science in the material sense over the next 20 years or so. To Abrams' credit, he wants to take this outside of the lab. So writing about the work that he's doing at the Lewis Institute, he says that yes, like we're doing these experiments, but they have the full support of all the cement manufacturers we're working with. And he says, crucially, the cement manufacturers understand that they can't just sell product, right? They can't just get away with selling product. Part of what they're selling also has to be the kind of service to the engineers, to the contractors, to teach them how to make a first-class product, basically, in the most economical manner. So Abrams wants to take what he's finding out in the lab and get it to the construction site. And the way that he does this is to merge his laboratory with a fledgling industry agency called association called the Portland Cement Association, one of a handful of kind of institutions that are looking at concrete as a new material, trying to market it, representing manufacturers, representing aggregate suppliers, and trying to get this material kind of out onto the job site in a way that engineers can trust and that contractors can handily place. PCA ends up being one of a couple of these institutes. The ACI, American Concrete Institute, is another that really push the idea that research into the material is going to make for a better, more reliable, safer product. And alongside Abrams' papers on concrete mixes, you can see that PCA is sort of all over the place, right? They want the kind of backyard builder to understand how to make and use concrete if you're making a driveway. They are interested in the architectural finishes of concrete, and they're also interested in how to make it better, both in the mixing yard and on the job site. When the Portland Cement Institute or Association begins publishing these, begins kind of getting that knowledge that is coming from Abrams' lab and elsewhere out there, you do start to see concrete being used more regularly in high-rise construction. So these are a couple of just examples of the sort of thing that's being published in the 1920s, both how to form the concrete, so drawings about how to make these mushroom caps that are crucial for the structural behavior. And then on the right, also the benefits of concrete. If you can use flat slab construction, you can get a thinner structural section, which means that you can get 10 stories in the same building height as you could get 9 stories in a typical post and beam system. And that goes for not only concrete, but it also goes for steel, and it even goes for timber, right? The concrete is going to give you a more economical section, and therefore a better return on investment. And in Chicago and elsewhere, but almost typically in Chicago, you see concrete being used in a variety of ways. The flat slab becomes the kind of default construction material for apartment buildings, especially where you don't have a lot of mechanical services. You don't need a ceiling void to distribute them. Sometimes this is a hybrid. The Edgewater Beach apartments on the left are a kind of steel and concrete hybrid. So there's a steel skeleton for much of this original building that is clad in concrete. So concrete still being used mostly as fireproofing. But for some of these other buildings, especially the shoreline apartments on the right, these are flat slab buildings using the latest technology, trying to find ways to increase the strength of the concrete to take up less space, not only in section, but also in plan, right? Trying to make the columns as small as possible. The Depression, of course, stops high-rise construction in Chicago of all types. And when it picks up again after World War II, we see concrete coming back in residential construction, especially in Chicago in these early, very progressive housing schemes that get designed by Harry Weiss, SOM, and others. They're interested in kind of squeezing the most number of floors into the minimum amount of height. And flat slab concrete, again, is crucial in doing that. More kind of middle class or upper middle class construction also uses this. Mies van der Rohe's first skyscraper, famously, is a concrete apartment building on South Lakeshore Drive. You can see in the digital reconstruction here that he's using a very conservative technique at first. This is a pan joist system, so it has drop girders, it has joists, it's less efficient than a flat slab. But in the second and third concrete apartment buildings that he does in 1949, 1951, you can see from the construction photo that he's using a flat slab. And this is a flat slab that now is about 10 or 12 inches thick. Columns are sized to take the punching shear, but also to take the load of all of these heavy slabs as they sort of come down the building. Interestingly, 86880 Lakeshore Drive, his most famous apartment buildings are steel. There's some evidence in the oral histories that the steel industry donated a lot of the material to make steel economical. But when Mies and the same client got commissions for the kind of sequel to 86880, 900, 910, the Esplanade apartments and Commonwealth apartments in Lincoln Park both used concrete. And on the left, the plan drawings, you can see that the steel is spatially more efficient as a column, right? The concrete is bigger. But in going in and looking at the drawings, what you discover is that the concrete is much more efficient in section. The 10-inch structural slab that it takes to span the apartments in 900, 910 is half the structural depth that the steel was to span a similar dimension at 86880. And with some kind of turning the floor to ceiling height down a little bit, you can see that we now have, instead of a 10-foot floor to floor height, less than 9 feet. And what this means is that 900, 910, even though it's about the same height as 86880, has 3 more apartment floors in it. So greater return on investment, better acoustics, et cetera, et cetera. Concrete in Chicago gets used for apartment hotels as well. So this building by Milton Schwartz, Executive House in 1960, was at 27 stories, the tallest concrete structure, tallest concrete occupied structure on the planet. So this is the first of those buildings after World War II that sets the record in Chicago. And it's nothing particularly special. It's held up by shear walls and columns. And the concrete at this point is about 3,000 to 3,500 PSI. So it's not a huge improvement over the strength of concrete before the war, but it's beginning to think about ways to deploy that material in more structurally efficient ways. The real kind of turning point is in 1961. And some of this is due to construction innovation, and some of it is due to kind of material science. The construction innovation comes about on Marina City, maybe the most like famous concrete skyscrapers of the era, certainly the most distinctive. And a couple of different factors come into play here. One is there's an architect, Bertrand Goldberg, who is super innovative and looking to create new forms, new building types in a way, and also to use whatever the most advanced structural and construction techniques he can is. This is like one of the first buildings that is conscientiously of the space age. So on the right, you can see those are slip forms, just like the grain elevator that we were looking at from the early 20th century. Those slip forms are slowly climbing, and they're basically building these two giant grain silos, exactly the same technique, continuous pours as those things climb up. The detail on the left shows McHugh Construction, the contractors, using fiberglass formwork to form these doubly curved balconies at the edge of the building. McHugh pioneered the use of fiberglass forms. They understood that the curvature that Goldberg wanted, not just in plan, but also in section, was going to require very, very complicated formwork. And rather than setting millions of carpenters to work on it, they built one jig, made about 60 fiberglass boats, basically, over the top of that jig, and then used those fiberglass forms again and again and again as the construction proceeded up the cores. Fiberglass forms left a better finish. They were also reusable a dozen or so times. And so McHugh really pioneered this way of creating complicated forms in concrete. Complicated forms that could take advantage of concrete's monolithic nature. So every piece of Marina City is connected to every other piece. And when the wind blows on one side, every bit of concrete is kind of feeling it. So the concrete is kind of all one piece. It's taking advantage of that monolithic behavior. And it's also being cast in forms, the cylinder being the kind of ideal column shape that are particular not only to concrete and slip forming, but also structurally ideal. The concrete being used is also at the time the highest strength available, 3,500 psi in the lower floors, lighter and lesser strength in the upper floors. It's about this time too that Abrams' initial kind of paper gets revised a little bit. A mechanical engineering professor at Iowa State, Herbert Gilkey, writes this paper in 1961, Water Cement Ratio versus Strength, Another Look, where he looks back at what Abrams was doing and says that Abrams was a little too quick to dismiss the idea of aggregate. And just, because like the family tree is so interesting to me, like Gilkey teaching at Iowa State was kind of fascinating because I spent a number of years teaching there. But it turns out Gilkey did study under Talbot and actually taught at Illinois very briefly. He had to leave because he married Talbot's daughter. And because of the state's anti-nepotism rules, that was not allowed. We do things differently downstate than we do in Chicago, very clearly. But to me, this is just further evidence of Talbot's importance, right, and Talbot's influence. That yes, there is in fact a very strong connection here. What Gilkey argued was that yes, the ratio of water to cement is vital, right? Abrams was right about that. But he says that there's a lot of strength left to be had by looking at the proportion of cement to aggregate and by looking at the aggregate itself. So what is the strength of the aggregate? What's the size? What's the texture or roughness of the aggregate? And how big can you get it? And this turns out to be key to the huge jumps in strength that we see in the 1960s and 70s. Some of that is geologic. This is the Thornton Quarry that for many years was owned by a company called Material Service Corporation. Material Service was owned by the Crown family, a big name in Chicago finance and in construction. For many years, Material Service was just sort of a run-of-the-mill concrete company in Chicago. But around 1961, around the time that Gilkey is writing his paper, they get the contract for the concrete for Marina City. And because Bert Weinberg, the engineer, is kind of pushing them to increase their strength, they begin looking at the methods or the ideas that Gilkey had, and they begin experimenting. Their yard, so-called Yard 1 in Chicago, is located on the Chicago River. So they can bring in aggregate from a wide range of sources, not only from Thornton Quarry, but they can experiment with aggregate from Minnesota, Michigan, other places on the Great Lakes. And it is only 15 minutes from the loop. So it's a short drive for the trucks to take the material to the job site, to get it placed, but also tested really rapidly. This becomes, I think, the most important concrete laboratory in the country over the next 20 years or so. There are two engineers working for Material Services, Jaime Moreno, who is an Illinois graduate, but in agricultural engineering, not in structural engineering, and John Albinger, who is still the subject of research and some questing. And together, they begin working with local engineers, local contractors. They begin experimenting not only with all of the variables that Gilkey is talking about, but with admixtures, in particular fly ash and silica fume, both of which are really, really fine powders that essentially kind of replace water in the mix, that make for plastic flowing concrete without adding a great deal of water. And in addition to supplying material to the job sites, Moreno and Albinger are part of this group called the Chicago Committee on High-Rise Building that is looking at all aspects of skyscraper construction throughout the 60s and 70s. In 1977, there is a task force report that Moreno is one of the co-authors for, and they basically published dozens and dozens of pages that show that by tweaking the size of the aggregate, the type of the aggregate, by adding fly ash, by adding silica fume, and by experimenting with those proportions, you can get exponentially greater strength, even beyond what Abrams thought possible. Interestingly, in the report, none of the aggregates are actually called out. None of the materials are called out. Material Service kept all that information proprietary, but they released the results of the test as a way of explaining to the profession that these have been not only tested, but they've been experimented with. We know when we send a mix out to your site, we know very precisely how strong it can get. And Albinger later writes that he saw that Material Services saw every job basically as a laboratory. So they would get a contract for a certain strength of concrete. They would say, we can absolutely do that. We've experimented with it. We can get 4,000, 5,000 PSI. But we also have this experimental mix that we think is like 6,500 or 7,000 PSI strength. Can we use that on your job site? Can we test it? Can we have it go through the same testing procedures that the normal concrete is going through? And can we see basically how it performs, not just in terms of placement, but also in terms of long-term performance, right? Does it behave the same way as the other concrete we've been sending you? Contractors agree to this, engineers agree to this, architects agree to this. And this becomes this kind of amazing back and forth, this collaboration between one materials provider in particular and the rest of the profession. This is a photo of Water Tower Place, a building that I'll talk about here in a little bit. Paul James, the site engineer for McHugh, talks about this basically as this ongoing conversation, right? Where because Yard 1 is literally right there, because Material Services is available, because the Portland Cement Association is just up in Skokie, that knowledge exchange was just frictionless, and that people were willing to share what was going on. Okay, maybe not the actual recipe, but to share the results they were getting in Yard 1, to kind of test it up in Skokie as a kind of independent test, and then to see how it was actually operating on the job site. And these then are those buildings that Carol and I noticed that were just sort of jumping up in height. 1000 Lakeshore Drive on the left is the first of these, 1962. So basically the same concrete strength as Marina City, all the way up to 311 South Wacker, which is a building that's about 750 feet tall on the right, and that set the record for concrete height in 1990. Between those, there are some iconic buildings like Point Tower, the kind of curvy Mies nod out by Navy Pier, and Water Tower Place, not only a record setter for height, but also a building that has a hotel, a shopping mall, 2 Broadway theaters, and a parking garage. So the concrete here is not only doing the sort of typical beam and slab or column and slab work, it's also engaged in these very, very long span trusses, for instance, over the theaters, which the architect, of course, put in the basement, right? The toughest possible place to put a long span. So you can look at these buildings as record-setting heights. And here you can see Marina City, 1000 Lakeshore Drive, Lake Point Tower, Water Tower Place, 311 South Wacker. All of those set records for heights, but there are also these buildings that Material Services worked on in between, where they were experimenting with high-strength concrete for other reasons, right? That the architect wanted the columns to be smaller, or that they thought they could get greater height with less area down at the base in concrete. Those buildings all set records for concrete strength. And even though there's a kind of basic relationship, this is now concrete strength instead of concrete height. There's a basic relationship between how strong the material is versus how tall you can go. Some of these were strong without being tall. And it's interesting and potential future research to understand why exactly that was, what happens on a building, for instance, like 225 West Wacker, which is a relatively small building, but use these apparently to get an adequate sized parking garage in a relatively tight space. This is just a piece that Albinger and Moreno wrote for a concrete textbook, where they're not exactly giving away the game, but they're showing how the experiments that they did in Yard 1 led to an improvement. As you can see, if you look at the parentheses, the numbers in parentheses down at the bottom, a 1 year compressive strength getting up to 17,000, 18,000, 19,000 PSI. So a good 4 times the strength that was available even in 1961. And all of this is just by adjusting the proportions of aggregates and adding these 2 kind of miracle additives, right? Silica fume and fly ash, again, which are making for a stronger mix by taking the place of some of the water that's in the concrete. Also, members of the Chicago Committee on High-Rise Building and contributors to the task force reports were Faz Khan and others at SOM, who began to experiment with this higher strength concrete in new forms. So if by now we've kind of answered Duff Abrams' question about, like, do we know enough about concrete versus reinforced concrete? Well, now let's flip the conversation again and talk about what reinforced concrete can do. And SOM and Faz Khan, of course, understood that the tube structure, the hollow column that forms the core, for instance, of Marina City, is the most efficient shape. If you can push all of the structure in a building out to the perimeter, you get a form that's naturally stronger. And so that firm looked not only at steel in tube designs, John Hancock Building and Sears Tower, but more of their tube designs were actually in concrete. So Brunswick Building on the left, which relied on a tube with a core of shear walls, and DeWitt Chestnut, the tall building on the right, which is literally just a concrete tube on the outside supporting apartment floors within. SOM recognized also the kind of possibility in formal gymnastics that you could get with a tube structure, and that concrete allowed in ways that steel didn't necessarily suggest. So One Shell Plaza, one of their tube structures from the early 1970s, which, even though it follows the kind of basic like boxy tube, uses concrete's plasticity to make these deeper columns where the loads are being collected and brought down to the ground over the entrance. More kind of formal expressiveness in One Magnificent Mile. So these are hexagonal tubes, possible to do in steel, but easier to do in concrete. And then on the far right, what I think of as the concrete Hancock Center, the cross-braced Ontary Center, 1986. This was Foz Khan's last building. It's maybe more known for that. But the idea that concrete, because it's monolithic, means that those cross braces can be formed as part of the frame itself, right? Not something that's added to it later. One set of architects that I've explored in the book that I think deserves a little more credit than they've had. This firm of Dubin, Black, and Matusami designed these tube structure apartments all over Chicago, South Side, Lincoln Park, North Side, where they took Foz Khan's tube idea and combined it with McHugh's flying forms in steel this time, not in fiberglass, but as a way to make the exterior of the building not only strong, but also quick. And high strength concrete here again plays a big role. All of those things that look like mullions in the facade are actually columns, and they are doing the work of holding the floor slabs up. By distributing the weight of the floor slab over many columns, you solve the problem of punching shear in the kind of opposite way as the big, heavy mushroom columns do. Another area that we looked at and that deserves further discussion is the idea of composite structures. So taking advantage of steel's quick construction and concrete's ability to serve as both the gravity and wind bracing systems. So here on the left, this is a Foz Khan tube structure that has a sort of peculiar interior. This is actually on the site of the Union Station head house that replaced the Western newspaper building that Abrams was able to test back in the 1910s. And because it's over active rail lines, the structural system that Khan developed was a concrete tube on the outside and then lighter, more flexible steel on the inside that could be woven down through the tracks. More typically, buildings like 70 West Madison or Oak Brook Tower use composite construction in exactly the opposite way. So a concrete core in the middle that started first and goes up, usually the basis for a tower crane, and then the steel work is built around it and catches up basically by the time the core reaches the top. Chicago is a kind of natural place for this for a number of reasons, one of which is that the Steelworkers Union in Chicago does not object to having workers in other trades above them, as they do here in New York. So the idea that the core can go up first, followed by the steel works in Chicago, as it doesn't maybe here. And that kind of expertise, I think of it almost as the kind of flywheel effect, that all of this knowledge about concrete, all of this collaboration between material services, architects, engineers in Chicago leads to this kind of culture of sharing, right? The Committee on High-Rise Building is one of these organizations. And you see that kind of knowledge, the knowledge of structural engineering, the logic of material science, architects trying to figure out how to put these two things together in some of the earliest super tall proposals. Some of them happen in Chicago, or the designs happen in Chicago. They're proposed for Chicago, and none of these three obviously are built. Miglin Beitler's Sky Needle, engineered by Thornton Tomasetti, which relies on a kind of strong core and then 4 pairs of giant pier walls on the outside. And more exotic structures like 7 South Dearborn in the middle, which is called a stayed mast, basically thinking about the building almost like it's a giant radio antenna, and the Chicago Spire, which Calatrava did with Thornton Tomasetti on the right. Even when super talls get built elsewhere in the world, though, the engineering has often been in Chicago and has often been based on the kind of concrete knowledge that accumulated there. Tower Palace 3 in South Korea was SOM's kind of prototype for the buttressed core that ended up structuring the Burj Khalifa. And we do have one of these, or a couple of these in the city, 401 North Wabash, SOM's building that they did in 2009 it uses concrete, high-strength concrete for an outrigger truss. 17,000, 18,000 PSI concrete, at least in the base. And then this innovative way of balancing or bracing the building as if the core were kind of holding ski poles to either side. So with a couple of unbuilt and a couple of built ones, I'll leave it there. It is interesting to me that 401 North Wabash and Marina City are literally 200 feet from each other on the Chicago River. And they frame about 48 years of architectural innovation, engineering innovation, but also concrete innovation, right? 3,500 PSI on the left, up to 16 or 17,000 PSI on the right. The fact that there is an absolutely classic steel-framed Mies van der Rohe building between them, to me, is just kind of the punchline to the whole thing. As Carol said, this has been this kind of glorious rabbit hole, and a lot of the people, the Chicago Committee on High-Rise Building is still active, and they were very generous in making me a member a couple of years ago. So I've been able to talk to some of the people, both who were involved in some of these buildings, but also people who remember people who were involved. And those conversations have been important in sort of scoping out what this story might be. Ongoing, lots of questions still to answer, but I think a story that answers some of the questions about why these buildings in that particular place and why that particular material. So thanks.
Hi, welcome everybody. I'm Carol Willis. I'm the founder, director, and curator of the Skyscraper Museum, and I'm delighted that those of you who are in the gallery could be with us tonight and online as we live stream, and as the video of this will be included on our website. We will add this lecture to the kind of encyclopedia of Tom Leslie's lectures for the Skyscraper Museum, because our frequent speaker and the collaborator on this exhibition in its last weeks here at the museum, the Modern Concrete Skyscraper, is the impetus for tonight's lecture for sure, but it was a collaboration that Tom undertook to guest curate here at the museum with contributions by Bill Baker of Skidmore, Owings and Merrill, to think about the material basis for the 21st century skyscraper, a building of essentially of concrete, and to find a narrative, a lineage that goes back all the way to the 1880s and the beginnings of reinforced concrete or modern concrete. And in the course of our research and in the strategy that we took in order to explore these ideas and the examples that found their place in the exhibition, we began with a lecture series that asked a lot of scholars who've been working in this field to take a building and to highlight the design and engineering and construction processes around these buildings. And it was those contributions that form the basis of the series on the Modern Concrete Skyscraper that I hope you'll, if you haven't seen it already, look at on our website. And so this is the last of that series, and it's the result of about 2 years worth of thinking and then compiling the material in this exhibition. And the research questions that occurred to us during that whole process, and especially Tom's digging and interviewing and searching for people who could be the testimonies, the witnesses, the original participants in many of the material innovations that he's going to talk about tonight. And as we looked at the history of the modern concrete skyscraper in the post-war era, so in the 1950s and after, it appeared very clear, and Tom will talk about this, that Chicago was a center of invention, innovation, and engineering and materials development and construction technologies. And Tom has brought these things together in the lecture that he'll deliver tonight in a way that I think really approaches new research questions and new avenues for thinking about the history of architecture through a materials lens, but also integrating construction and engineering and kind of commercial and trade association contributions to this mix. Tom is particularly well positioned to be bringing this approach to the history of architecture because he is himself an architect. He teaches at the University of Illinois at Urbana-Champaign. He teaches both in studio, so issues of design, but also the history of construction. So and he has written about the engineer Pierre-Luigi Nervi. And so in all of these dimensions of his scholarship, as well as his practice, he really has a unique perspective as an academic on this material, but he also is a tremendous expert on Chicago. And I'm holding up just the second of his books on Chicago skyscraper, which covers in the second volume where he left off in volume one from 1934 to 1986 on how technology, politics, finance, and race reshaped the city. So the Mr. Chicago skyscraper is here in order to explore the importance of location and influence in the innovation of the modern concrete skyscraper.
You definitely talked about it a bit, but could you remind me what about the concrete pillars allows the floors to be so significantly thin versus some steel?
So the way I think of it, this is an architect talking, right? There are engineers in the crowd who are going to laugh at this. But steel is strong because of its shape, right? We can take the material and turn it into a very, very efficient shape, right? Concrete, we're stuck with a fairly crude way of making it. So concrete is strong because of its bulk, basically. And the reason that a steel I-beam is strong is that it's deep. There's not a lot of material to it, but the material is in the places where it's going to do the most work. And that means a tall beam that's able to kind of resist bending a lot. Concrete, we can't do that so easily. So we just throw as much material in as we think we need. And it's the bulk of the concrete that makes it work. So that concrete floor is much, much heavier than a steel floor, but it's much, much thinner. And so an architect's way of thinking, like that's the trade-off.
Got it. Thank you.
Yeah.
But at the same time, could you talk about the kind of philosophy of a minimum use of materials as a both architectural and engineering idea and how that plays out in concrete?
Yeah. So if you think about both materials, right, steel and concrete, if we're paying by the pound, right, we want to use as little material as we can. Steel per pound, the cost per pound is a lot more expensive than concrete cost per pound. So we have to do more with it, right? We have to put the material only where it's doing the work. Concrete is a material, relatively cheap, right? And so we can afford to throw more stuff into the structure to make it work. Chicago, though, at least until the kind of early 1900s, is the exception because we are trying to keep buildings very lightweight, right, to perch them on this very bad foundation soil we have. That, I think, is one of the reasons that steel becomes so popular in the city, that it's lighter than concrete in terms of its weight. By 1900, we have caissons or deep well foundations that just go all the way to bedrock, and it doesn't matter so much. And it is interesting that is when Chicago goes, oh, concrete maybe is one other way to solve the problems.
Could you discuss seismic issues, especially in areas which are most vulnerable, concrete contrasted to steel?
Sure. The question is about seismic and how concrete performs versus steel. Concrete generally, with today's philosophy, steel is more ductile, right? It bends, it doesn't break. And concrete is necessarily brittle, right? It breaks instead of bends. So steel is generally, I would say, more popular in places that have serious seismic conditions. One of the projects that I worked on in practice was a laboratory in Palo Alto that was 2 miles from the San Andreas Fault. And our engineer said, it's going to be in steel. And the laboratory director said, we have very sensitive equipment. It has to be in concrete. And this ended up being like the most ginormous concrete shear walls imaginable, right? Basically to make sure that the building just like stuck to the earth and didn't, wave back and forth. So it is possible to design seismically in concrete, but you do end up sort of chasing your tail. And again, building with bulk instead of with kind of finesse. Steel, because it is ductile, is today generally considered the more favorable seismic material. In the back.
I've been to Chicago a number of times, not recently, and I'm wondering, are there any significant brutalist buildings in Chicago? I mean, that would be concrete, right?
Oh yeah, yeah.
Are
for
there any
sure.
biggies, so to speak?
Well, some would call Marina City. The question was, are there brutalist buildings in Chicago? Some would call Marina City brutalist, right? If you're thinking about like the exposed material, the kind of, very, very strong forms and concepts. Right across the river from Marina City is 55 East Wacker. It was originally a headquarters for Blue Cross Blue Shield, which is, I think of it as the best building Paul Rudolph never did. It is the best building Paul Rudolph never did.
Right.
It's a shameless Paul Rudolph knockoff, but the concrete is gorgeous, right? Absolutely beautiful, like corduroy concrete. Was done by C.F. Murphy, like old school Chicago firm, and their designer Otto Stark was a huge Paul Rudolph fan, and he kind of got away with one.
What year was that in?
That was about 1968.
I'm sure I've seen it.
Yeah. And the other, like when I have people ask me about brutalism in Chicago, I say, well, go to University of Illinois, Chicago, because the whole original campus was all done in exposed concrete. The administration tower there is, I think, as good a brutalist skyscraper as there is. And the Walter Netsch, famously, the architecture building is just the most impossible building in the world to get around in. And that, I think, is maybe the best example in the city of that.
Isn't that where they filmed the horror movie Candyman?
I know they used their housing projects that are notorious for having had that film there, but the UIC campus is a film set waiting to happen if it hasn't already been used.
And could you say a word about the trades and how many workers were available, or if that kind of labor statistic plays anything in the adoption or the economics of the building?
Yeah, this is an area for further study for sure. The economics of labor, steel is quicker, but it requires very skilled, very expensive workers. Right, concrete is generally a lower skilled trade, but making the formwork is expensive. But as McHugh found out, if you can find ways to mass produce the formwork, you take some of that expense out of the equation. Chicago has always been a really strong union city, and with that comes a lot of education in the trades. So there's always been a skilled workforce that's able to do some of the complicated things that are required. But that, I think, also is one of the reasons, especially today, that concrete is a popular material in Chicago, is that those workers are less expensive than steel workers. And as we've seen the kind of strength and also the speed of concrete pick up, labor has become a bigger part of the equation. But that, as I said, like that deserves some digging into. to figure out more.
We have a question from one of our YouTube watchers,
Great.
Kevin. He wants to know a little bit about the pumping technology for concrete and what impact that had on the ability to construct tall concrete buildings.
Yeah, Carol and I had we had thought about one whole part of the exhibit being about how the technology has evolved, and how you get concrete up high is a big issue, right? If you have to take a bucket of concrete up 100 floors, well, that's 15 or 20 minutes that you don't have to get concrete to the site, right, or to test it on site. So concrete pumps are a thing that comes about in the I think late 1960s, if I remember our research right. And it gets gradually better and better and better, so that through staging, right? So you pump up however far you can, and then you have another concrete pump that takes that and puts it up further. And you couldn't build the tallest buildings that we build today without it, because just simply of the time it takes to actually hoist a bucket up. The other thing that it allows is continuous pours, right? You can keep the pump going instead of having to wait for the next bucket to show up every time. So how the actual technology has evolved is probably a longer, richer story that deserves to get told. But the basic principle is that allows you continuous construction, and it allows you to speed construction in the upper floors.
Any other questions? No, in that case, we can have a thank you to Tom again and a drink over at the reception.
So thanks.